Well, thank you for asking me to do this. When Milton was talking about some of the knowledge that existed but wasn't captured, and if it wasn't captured, it can be used. About 2 weeks ago, I was in D.C. I'm working on this constellation SRB nowadays, and I know Handley was all struggling with this effect of these thrust oscillations, on the hardware, on crew, on tanks, on baffles in the propellant tanks. So I was very proud of myself. I said, "Hey Jay, I've got a present for you," and typical NASA guy, when the former contractor brings presents, you have to be skeptical. But I said, Jeff, I don't know if you know that or not, but during 80s, we at Rockwell with NASA have done a test where we put a couple of crew people on orbiter seats and put them on this big shake table and did some transfer functions. We shook it, so according to some acceleration profile, at the base of the seat, and we got a response of this crew seat system. And guess what? We found that all these hard-bodied astronauts that we think of them as made out of steel, when you put them on a shake table, they behave like flab. And the critical damping ratio for that system was like of order of 20%. And all the analytical folks who are predicting these crew responses of several Gs, they are using 1%. And in a steady state response, damping is the very important parameter. So he was very happy, and I said, just go and tell your people to go and get some reports from it, and they can use this knowledge to maybe you have to repeat the test, but at least you will be able to use higher damping, and that will clear the concerns for the crew. Well, 2 weeks later, says, I talked to one of Henley's people who does structure. He says, we can't find any traces of this test. So I finally woke up some retired guy from Rockwell, Phil Schutz. I said, Phil, you were a vibroacoustician, and they did this test. He remembered a little bit, but the pathetic thing was that NASA paid for this test. They used it. We used it during shuttle, development phase, but doesn't exist. No traces, no reports, nothing. And so NASA will, and it's to repeat this test still a hell of a less expensive than designing some absorbers or springs or dampers or dash pods or whatever, to attenuate the response of the crew. So that's just one little example, how capturing something and making it available helps. Dave and I had another discussion to make sure that actually users consume it and use it. It's another challenge. But in this case, we couldn't even find the traces of a good old NASA test that was done by, I used to work for Rockwell as a contractor, and it disappeared. There was no mechanism. We had like instant satisfaction. We did the test, users coefficients, did some analysis, and then somebody disposed of it in a filing cabinet, where we moved from one location to another. So you guys, I hope, you will preclude that from happening in the future. But that's a little bit of it. He asked me to tell about myself a little bit. I came to Rockwell in '74, and is because they just want this big thing called space shuttle, and I wanted to, I was an immigrant from Poland, and I thought, boy, that would be pretty neat to get synced up with this, this American aerospace industry. And so I came to Rockwell, and I remember this. So I lived through the whole development of shuttle. I was loads and dynamics guy, and then I became ultimately program manager for the system integration portion we did for NASA. And then when Boeing bought space business from Rockwell, they listened to me talk, and they say, well, that guy must speak Russian, because the way he speaks English, he must speak something else, My Russian wasn't all that good, but they asked me if I'd go and build sea launch. I didn't build anything. I was trying to help Russians, Ukrainians, and Americans and Norwegians to work together and have them believe that I can actually pull it off. So I did that for about 5 years. We brought the system to Long Beach in California, and it's online. And then I had so much fun doing sea launch that somebody at Boeing decided that guy is having too much fun. So they asked me, he says, hey, how about you relocate to Houston and run shuttle orbiter? Because I guess we are trying to relocate some people. So You know, I said, wait a minute, I'm having too much fun here on the sea launch, you know. My Russian was perfect by then. I could do a TV interview in Russian language. And so they screwed it up for me, and I came here, and I worked on Orbiter. And then about 2 years ago, you know, I'm 68 now, and I was thinking, I've got to retire one of these years. And I'm thinking, you know, we went through so much pain during shuttle development, and I mean like pain, when you go home and you can't sleep because something went wrong, and reputation as an individual, as a contractor, as your customer's reputation was suffering. Press was ripping us up, and I mean, it was like bad. And I was thinking, you know, I'm going to retire, then some of this pain was just going. This is before your team came about, you know, it was like 2.5 years ago. And I was thinking, well, you know, in a little way, maybe. So I went to Rockwell, to Boeing, rather. I say, give me a little discretionary money. By the way, I still have, the only reason I have Boeing logo here, because last night I didn't know how to remove it. You know, I'm retired. I've retired a year and a half from Boeing, but these charts some of these charts were developed when I was a Boeing guy. So I said, you know, what if I just take like all the guys my ages, you know, my generation, where we used to wear, you know, short sleeve white shirt with all skinny ties and, you know, protector for our pens, you know, in the pocket. The guys from that generation. And we sort of scooped out all these painful lessons and made this 2-hour briefing. And I walked, you know, flew around NASA centers, and I talked to all the management. The only guy I haven't briefed is Griffin. Somehow, you know, I was at ESMD quarterly, and he was there, and he had to get on the plane, so I never briefed him. But other than that, I briefed almost everybody. And first thing that I observed is the guys loved the briefing. Oh, because it was very humble briefing. It was like spilling your guts of all the screw-ups we did for NASA, you know, and with NASA collectively, because we're all these know-it-all guys, you know. And what occurred to me, that talking to management is wonderful because they are like sophisticated guys, smart, you know, but they don't really, they can use this stuff. That stuff has to go to the people who actually, like if you talk about structural dynamics problem or avionics problem, you've got to transfer this knowledge to the guys who are working on that. You know, talking to Doug Horowitz, who says, boy, this is a great briefing. That makes me feel good, but it doesn't accomplish much. So finally, Steve Cook asked me to get that briefing to all hands on Ares. And I felt like for the first time, you know, I'm actually talking to the guys who can perhaps use it. Although we Americans, you know, we are blessed with this wonderful quality that some people call arrogance. It's very difficult to us admit that that we need knowledge from somebody else. You guys maybe are breaking that mold, but that, you know, it used to be that people just don't, you know, I'm educated, I know my stuff, I'm a professional, I've got some awards, you know, why is it I need to have some input from sides, you know? And then we go and make mistakes, the same mistakes that were made in the past. And I don't know. I've done this briefing, not this briefing, this 2-hour briefing, I don't know, maybe 25 times at most of NASA centers, and I don't know if I made any dent at all or not. So what I did, when David asked me to come here and talk to you guys for a little bit, what I said, okay, so I took that briefing, and I just selected few things. And I said, okay, let me examine the lessons we learned from shuttle. Is it being reflected in some actions on Constellation? I mean, you know, we learned something painful. Okay, there is a new generation of guys working on there are some common things, you know, lift-off event, the ignition of SRB, it's same SRB, it might turn out a little different. For Ares 1X, it's the same MLP, later it will be a little different MLP, but have this lengthy, expensive, painful learning process. Has it been at all translated to the new guys, and are they showing in their actions, you know? So that's what I try to do here. So, you know, I'm going to, once we go ahead through this, and like I say, I apologize. I'm not a Boeing guy anymore. I'm not all that computer literate. I used to have somebody to help me. I'm retired now, so, you know, so I didn't know how the hell to remove it, so it's still here. So don't think I'm speaking here for Boeing or Sea Launch or whatever. I'm just a private citizen. Okay. So what I try to do is I had like about 35 of these powerful lessons learned. Each one was some of them were good, most of them were bad experiences. Some of them saved money and brought not glory, but at least satisfaction to NASA customer guys, and the other ones were painful and expensive. So I'm going to look at some structures and loads area in avionics and design for operations. And this is probably like a foreign language still in American aerospace industry, and I'll talk about it. And then I'll talk about margins. I just picked several, 4 areas out of these 30-some lessons learned, and see how we are doing. And I'll just give you my conclusion. Now, I'm very familiar with what happened on shuttle. I'm less familiar because I'm chairing this Constellation SRB, so I see I have snapshots of what's happening, and I talk to people, But my view of how is stuff being implemented in Constellation is less in depth than it was on shuttle, because I worked that and I lived it and suffered through it. Go ahead. Okay, this is just, and Dave said you guys have, I guess, my old 2-hour briefing, but this is all the areas that I dealt in the original briefing, but I just selected those 4 areas that I just showed you a moment ago. Go ahead. And the whole idea, could you go back for a second? The whole idea in this thing is, these lessons learned, hey guys, you NASA paid for it already, for these painful lessons. Don't pay for them again. This is like a map to a minefield. I come here with all the bloody legs, and I said, find your own mines to step on. Don't step on the same mines, So that was the whole idea, to give you a little bit less expensive, a little more reliable, a little safer system, like I say. But if you ask me, did it make any difference? Hell, I don't know. Maybe a little bit. Okay, so let's go. So mainly problems, some success story were included. And by the way, I'm talking about things I knew about. Some people say, well, why don't you include station? Well, my involvement in station was peripheral. Why did you talk about Apollo? I said, well, hell, I was in Poland, minding 2 cows that we had in our little farmette, So I don't want to talk about things that I didn't. I'd rather limit my conversation on things that I know about, And this is shuttle and a little bit of Sea Launch, because Sea Launch brought some things that we could have learned, but I'm not sure we have. And I'll probably go to my deathbed one day thinking I should have given more of these damn briefings to NASA, but okay, let's go. If you look at the shuttle elements, there are some real commonality with Constellation. The booster, when you ignite it, you have the same physics happening as it did on shuttle. And it's a different configuration, but there are some things that are very common, and the lessons are very applicable. Go ahead. So, okay, let me go through like first area, technical area that has. Go ahead, David. I'm going to look at and this is from my original briefing. Okay, we have the finest aerodynamicists from Rockwell, from NASA, and NASA. We did not have 10 centers involved, but we had Marshall, JSC, aerodynamicists, and our own from. And so we do all this analysis, we do all this testing, and then we fly. And we actually broke the vehicle in one area. We had this huge overpressure wave hitting the vehicle, and we thought we had it attenuated. We had water injection, and so we actually, there's 38 or 39-inch nitrogen tetroxide in a forward fuselage tank that we buckled one of the struts that was holding it because of the dynamics of the vehicle response due to this overpressure. We did not fail it. Can you imagine trying to flying ascent with this thing rattling in there, I mean, this was, I was kidding. They're saying God must be American because we screwed up, but he protected us from our ignorance, So anyway, we survived the flight, we landed, and then so we found that that our finest aerodynamicists thought that why don't you go ahead to they just simply misread the source of the ignition overpressure. In typical response to a problem, you know, we created this wave committee with NASA and contractors. We had this model at Marshall. Marshall was, by the way, involved very much, and this is where I think you will see that this lesson is used on, you know, getting ready for the Ares flights, simply because I was telling David, wonderful way to transfer information is sort of like playing contact sport. If you're involved in it, you get the knowledge. If you are not involved in it, it's up to you to sort of go to somebody's shelf or somebody's computer and extract it. If you're in it, you know, and Marshall was in it, so that lesson is with them, you know, on Ares. But we finally fixed it. You know, we put those water troughs filled, you know, with water that absorbs some of the thermal energy and also the energy from the wave. And we have reduced it. We have solved the problem between STS-1 and STS-2. But the key mistake was that all the analysis was showing that the source of the ignition overpressure wave was going to be when you have these 90-degree turns. In other words, the gases hit the floor, and when they turn, this is supposed to come back as a big wave. Well, the STS-1 showed us that the source of the ignition. So, by the way, we had all the water injected in the wrong place, and we almost, you know, almost broke the vehicle. I mean, that's, and so of course, once we learned that the ignition source, I mean, the source of the overpressure wave was just at the exit plane of the SRB, and you know, and our finest aerodynamicists sort of, you know, looked at their shoes for a while. And concluded, yeah, we just screwed up. We were wrong, you know. And another thing is, like, compromise was made. Tomahawk was a little solid propellant rocket that was used to characterize this, measuring PC rate rise and what it means to aerodynamics, you know, the pressure wave. And that was, it turned out that the little Tomahawk motor had a different characteristic from SRB. But it was compromised, and people say, well, you know, that's all we've got. Well, what we had, did not represent shuttle, so we almost broke the vehicle. Okay, so let's go past it. So this just shows you, this is that somewhere on the body flap. Export compliance people had me remove some scale, so some enemies don't figure out what we did. But anyway, this is STS-2, pressure across the body flap. This is STS-1. And so let's go. So it's a big driver in lift-off environments, and for Ares, it should benefit from what we have done. And if you change MLP or propellant properties, you got to do something. You got to relearn this thing. So let's take a look at how I see on next chart. I think that this contact sport of us playing with Marshall guys had them, you know, this is continuity of MSFC involved. So they know about all of this, you know. And for example, I know that for Ares 1X, which is from the same MLP as we flew, they are actually going to go with the same protection. You know, it's a 4-segment SRB, water trough, water injection in the same place. So that piece of knowledge was transferred. Where those knowledge was transferred simply because people were there with us. And, you know, utilization of legacy hardware makes it easy. So it is the one that lesson learned is applicable and it's being applied. You know, that's easy. That's a good one. Let's go to the next one. Okay. Another one that we also had in STS-1, it was a big deal that could have failed the vehicle, but it didn't, because, you know, somebody was looking after us. Remember that? We had plume simulation trying to get the aerodynamics at ignition and during flight. Compromise was made, you know, hot plume test is expensive. You can only do it for short periods of time because you burn out your facility. So So they say, well, you know, cold plume, it's close enough, probably, most likely. That's another aero. See, somebody think, I hope none of you guys are aero guys and thinking I have like grudges against aero guys. But that's a reality. So, okay, good. So we fly, you know, STS-1, the data comes back, and boy, we had some huge negative margins in the wing, in the orbital wing. And also vehicle flew funny, you know, lofted, wound up flying like 10,000 feet higher than we anticipated, and people would say, what, you know, what, is guidance wrong or what? No, guidance was, you know, first stage is an open loop guidance, so it was because of this aerodynamic database. And this whole thing it was compromised. It was thought that cold plume test is good enough, and it wasn't. And so, you know, after the STS-1, we did do some, you know, it's expensive, but we did a hot plume test, and we fixed these predictions, you know, and what was interesting is it simply turned out that thermodynamics of expansion of these hot gases is different than for cold gases. And shuttle was more susceptible to be affected by, because we've got at the end of the vehicle, you know, we've got these 3 SSMEs, 2 solids, and you've got all these surfaces, wing and elevons, you know, and body flap and all that. And that was affected, of course, by these forces, different aerodynamic forces. So Ares is a little simpler. So let's go. So I'm saying that although the hot plume recirculation is not as critical, but you really need to address it so you, again, don't, you know, because your pressure distribution at the aft end of the vehicle is going to be different. And recently, and this is in my job, you know, pitching in as a SRB guy, I was listening to some Orion guy, and I said, are you guys using, you know, are you familiar with the anomaly we had on STS-1? And I was pleased to say the guy was familiar with it, and they are fighting with their program management to get funding to do some hot plume test on Orion. Because there is, again, you know, you on entry, you can be very much affected by how these plumes expand. So on the next chart, what I see is, okay, you've got a simpler axisymmetric configuration on Essence, so it's maybe less critical than shuttle. Marshall is a little less involved in this, so on Ares side, I don't know how well they are doing learning from our experience, but I was happy to see, because Orion contractor is JSC contractor, and JSC was, you know, down in mud with us when we were working the problem. I think the hot plume testing is contemplated on Orion. So at least the way I see it from my knot hole, at least the transfer of this experience through JSC to their contractor has occurred. And it's not all that clear how it's with Ares, but then there it's somewhat less important. For whatever it's worth, I gave my briefing to the guys on Ares about 3 or 4 times, so I'm hopefully they will do enough, considering that their challenge is a little less. Go ahead, next. Okay. The next one is structures area. Go ahead, next chart. This is one thing that and I don't want to claim credit for shuttle teaching constellation anything here, because sometimes right things happen. They look like they are correlatable, but they are not. They are just smart people are doing the right things. But throughout the shuttle development, especially orbiter, we were always maintaining 1.4 safety factor, and we never had, and our structures guy, loads guy, dynamics guy, we never had any additional margin. So as we do testing and we learn and things change, models change, you know, predictions change, some of the loads go up, some of them go down. Those that go down, you rarely have a chance to redesign structure, take the weight out. But those where loads went up and you have negative margin, you don't have any choice. You have to redesign. So your weight keeps bulging up, you know, because you have to put mud kits and doublers and whatever, you know. But we never had any margin to give up, and simply because shuttle started way in the hole performance-wise. And I'll talk about that later. So as the math models and definition of environments kept maturing, resulting changes, these changes always hit the hardware. And boy, I tell you, I remember seeing NASA program managers, Arnie Aldridge or Tommy Holloway, like hyperventilating, hearing about another 13 mud kits we got to put on the vehicle because we did some loads analysis. There was no margin to cash in. You know, program managers say, okay, you structures guy, here is your token for little margin. Don't redesign anything. Here it is. But there was no additional margin, just over bare 1.4 safety factor. So you kept redesigning, kept putting mud kits, and it was tedious, embarrassing activity because you have to stand down the orbiter. Plus, you are starting to convert ground up site, you know, KSC, into an orbiter repair facility or modification facility, which is another story, a drag on operational folks. So, but like I say, the tedious process worked. We flew safely, but boy, that created a lot of havoc and stand down and bad press. Go ahead. So lesson, you know, from that was, for the environments which are not well defined, like aero, like dynamics, like, you know, pressure loads are easy, gravity loads are easy. You don't have to have any safety. You're always smart enough to do those right. But especially aerodynamics and structural dynamics, they're always wrong at first. And I can say that because I'm one of those. I used to be one of those guys. So I'm saying, start with some additional factors. And the method of structural margin management could minimize costly hardware, could eliminate program stand downs, but they'll probably give you a little bit heavier structure. Well, shuttle didn't have the luxury because we are so much in a hole. We started out about 10,000 pounds in the hole performance-wise. So we never had any margin to give anybody, and so that's why NASA paid, and we kept embarrassed, but we flew safely. So suggestion is, try to use some structural margin management system. So let's see what I see is being done. They actually are doing, I think they're doing a pretty good job on this. And like I say, it's not maybe because we learned something from shuttle. It may be just today people, maybe they're smarter, maybe they, although maybe they listen to these briefings, I don't know. But they have margin management on Aries, and they have these growth weight allowances. And Orion is in tougher spot because they're really struggling with weight. But regardless of that, they actually do have this smart growth allowance implemented, which we didn't have on shuttle. So, like I say, if I was a little more arrogant than I am, I'm a pretty humble guy, I would say, oh, see, they learned from us. No, I don't know if they did, but they are doing better than we did in structural margin management. Go ahead. Okay, the last area is lift of loads, and this is just in a nutshell. What happens is, when you ignite solid, the SRB growth instantaneously, a matter of milliseconds, growth by 9/10 of an inch. You know, just grows because of the internal pressure. And so the way you accommodated growth, MLP deflects a little bit downward, and the rest of it jerks the forward interface. And for shuttle, this load, the forward interface is in front. This is where you take axial load. So then you go through this big hydrogen tank spring and dump these loads to orbiter. So orbiter is being propelled by these growth forces indirectly. Go ahead.
Question about the last one. Isn't, I'm guessing the real lesson from that factor of safety discussion was, over time, as you saw more data, you realized that your models weren't as well founded as you thought they were initially, and you miscalculated the loads and the factor of safety, and so you had to keep going back and adjusting.
Right. Yes. Yeah.
So the lesson learned maybe is that this reliance on physics models and analysis, and how there's so much uncertainty in there, and that real data and experience helps you realize.
Yeah, that's another way to look at it. You have a right way of looking at it. I just said it my way, but besides being you're wrong for a reason. I mean, one of this because maybe you are ignorant, you didn't do that stuff right. But another thing is that as program matures, you do testing, and you discover things in tests that are a little different than you do. So you tweak the models, and then you do aero testing, wind tunnel testing, and more sophisticated wind tunnel testing. So there is a growth of knowledge of precision, and all of that is cumulatively affect how well you predict these loads. And so there's probably more than one way to state the lessons learned. But the bottom line is, if you want to protect for whatever sources of your ignorance are, for not so easy defined environments, use some additional margin. And Shuttle couldn't do it because we were 10,000 pounds in the hole performance-wise.
The reason I state it that way is if we're learning a lesson in Constellation, then we probably have a whole lot more actual test experience than we're planning in order to better calibrate all those models.
Yeah.
Because actual experience is what helps you to calibrate.
Yeah. Models are a wonderful thing, and I allow me to take 15 seconds to say something that bothers me about something that happened lately in America. You guys heard this subprime fiasco in America, right? In financial, nothing to do with NASA. These damn banks have just as many computers as you have at NASA. I don't know if you know that. They have robust risk management that you wouldn't believe. And if you ask yourself the question, and I call these radio stations, I get on the air, I said, why is it that these smartest 30 American leaders of these institutions managed to lose like 2/3 of $1 trillion in a matter of a few months? Explain it to me. And you know what the common answer is? First of all, people sort of don't quite know how to deal with my question. And by the way, it is about 2/3 of $1 trillion. They already write down like 350 billion, and another that much is ahead of us. And you know what the common answer finally binds up? It's arrogance and reliance on these sophisticated models that make us so much smarter. I'm not implying that this is our problem at NASA, but my point is, and you brought up a good point, this arrogance and reliance on my models, I think we have to be a little skeptical. We have to move away and sort of like, hey, you who don't know the models, use your common sense. What do you think? And I think NASA today is doing that. That's why I'm here. That's why I'm, old guy doing a job on SRB, trying to stay aside and don't get in the middle of these analytical efforts. Just look from the outside and see if some of this is maybe looks screwy. So I think NASA is doing better than our finest financial institutions, by the way. So anyway, okay, so where did we go? So Aries, the growth of the length of the casing gets immediately dumped to the second stage. And I was cautioning at that time. I said, well, by the way, this took us 3 years on Shuttle to do this right. And it was all kinds of, we learned, for example, first of all, this is much more complex than that. That one is more susceptible because it's close connection between growth of a solid and the second stage. But we also had at Vandenberg, we learned another thing. It took us like a year of grinding, of churning out these Cray computers, times, to find out that if you go from a soft MLP to rigid pad in Vandenberg, your loads go up by like 30 or 40%. And so when I was briefing that, I said, when you guys are going to redo your platforms for the Aries, especially Aries 5, please pay attention to that. Don't get surprised. Don't start putting concrete, and then a year later your analyst will tell you, oh, gee, you can't fly because our newest loads are, 30, 40% higher. So, but I think that they are they know this. Here is again contact sport with Marshall guys. They were party to this, to solving this problem. Before we go to the next chart, let me just point one. When I was doing this, I was cautioning about this liftoff problem. Well, that hasn't, turned into a rage. What has turned into a rage is response to thrust oscillations. Because of this close coupling, you see, thrust oscillations in flight is no big deal for shuttle. It's different kind of a coupling, different dynamic property. Here you've got this straight, exciting axial mode of the second stage by these thrust oscillations. So that's where they got bit, not at liftoff. But it's because of the same configuration concerns. Go ahead. So I guess I already told, we solved that problem. Lessons, I said, in spite of the relative, and this is a case, these charts are like almost 2 years old, in spite of the relative configuration simplicity for Aries, liftoff loads may be significant design issue. Well, it turned out that they handled that right, but they got bit on these thrust oscillations. But again, because of configuration. Go ahead. So what do I see? Marshall again was involved in liftoff loads resolution, so there is continuity of knowledge, and they are in charge of all these Aries analysis. So that works pretty good. They are sensitive to the MLP stiffness, which is good. And the guys at the KSC likewise, I harped on that. I said, when you guys start looking, please pay attention to compliance of the new platform, so you don't hit the flight hardware by too stiff a platform. By the way, you can't make it too soft. If you make it too soft, the damn thing will be too susceptible to winds. You have this, so it's a tricky thing. But at least we are conveying those things, and sometimes it sinks in people's mind. And also forcing function. For liftoff, forcing function definition took us forever, to get it right. You see this big cocoon, where you have pressure growth. Some of this pressure pushes on the forward bulkhead, some of it goes out the hole, some of it pushes on this partial aft bulkhead. It took us forever. And I actually recently, a guy ran me to how do they do forcing function. They do it exactly like we did in the shuttle, finally, after struggling with it for a couple of years. Okay. Day of launch I loads. How are we doing on time?
Fine. We're going to go down to 7 tables, so we're good.
Okay. Oh, day of launch I loads. That's another thing. I don't know if do you know what I'm talking about? Day of launch. Does anybody here know what? This is where you try on a day of launch, get coefficients, trajectory coefficients, so you can fly with the minimum aerodynamic load at high Q. And it took us 10 years to figure out, not 10 years, hell, it took us, I'll show you a chart, it took us from 75 to 90s, like over 20 years to do this thing right. And I remember I actually briefed Arnie Aldridge at one time, and I could see he looked at me like, you guys are evil, We were just dumb, we were not evil. We just didn't know. And so we tried to work with our NASA buddies and come up with gin up these solutions that give us a little better launch probability. Once you go to the next chart. See, I'm generous, he said, we had at like initial stages of shuttle, before STS-1, we actually had much less than 50%. It was like maybe 20, we couldn't fly, basically through the winds aloft at high Q. So corrective, okay, we led this, and I call it evolution. This is like 20 years evolution we started design in a very naive fashion. We call these synthetic winds. We ginned up some winds that they were from measured winds. We collapsed them into like a handful of synthetic winds, and that's how we designed shuttle, to fly through high Q. And then Marshall guys show up with like thousands of measured winds, and we started to use those measured winds, and we couldn't fly through most of them. And by then orbiter is designed, the rest of the hardware is designed. So we let this, so we finally found, okay, and what it really is that winds vary a lot, you know. Sometimes they blow this way, sometimes shear content is like this, sometimes gusts are like that, you know. So they're all different, and what it boils down to is you would like to know on a day of launch what does a wind profile looks like. But if you design something for a generic winds, you have to really design for the broad range of winds, and that gives you either a heavy structure, a lot of, you know, or very low launch probability. Well, in our case, it was very low launch probability. So, but we went through this process. So we kept, why don't you go to the next chart? This little schematic shows, and this is, believe me, those are real decades, 70, 90, 75, 85, 95. We started to say, okay, maybe we can recognize that each month have a different wind. So that got us to monthly, you know, after seasonal, 2 seasons, then monthly, 12 months. So for each month we had a different set of these coefficients called I loads. And then we finally, then we came to alternate, and it's called alternate. You guys may not know what I'm talking about. Now, depending where the winds would blow on Q alpha, Q beta profile, we designed 9 trajectories. And this what shows what it does to the cost. You have to certify 9 sets of trajectories so that on day of launch you measure wind with a balloon and you pull the one that is closest to any of those 9. So this is like nightmare, you know, from program management and paying for it. It was terrible. So we finally got this, and this is where it was like emotional, big step. How do we convince ourselves and NASA, our customers, and, you know, is that it's okay to, like, few hours before launch, you have enough confidence to do these day of launch I loads. In other words, design trajectory to fly through high Q on a day of launch. And we finally did it. We had some independent processes, you know, checking one another. But today, go ahead. You know, today it's a state of the art. There's no suspense anymore, and they are using it. And so what it means is winds, and that's what I actually recommended in my two year ago briefing. Commit yourself. Steve Cook used to tell me, well, you know, why don't they just design rockets so you don't have to have these balloons every day, or, you know, measuring before flight. And I said, that's a wonderful idea. And I've seen a rocket like the Soviets designed it, called Zenit, the one we use in Sea Lodge. But believe me, you pay a lot of weight for it, because you got to design to be able to fly through any wind profile without designing the trajectory constant to mimic that wind profile, you know. So I said, you're better off committing yourself today to do a day of launch I loads, and that'll shrink, they'll skinny down your rocket a little bit. But that's what we are heading, and you wind up with the same vehicle being more robust because your wind dispersion occupy less of your structural loads, you know, because you fly in such a way that you minimize high Q loads because you know what the winds are. So that one, I think it's a given, you know. And like I say, I don't want. And this one probably came from the shuttle experience, you know, because the whole community was witnessing this for 20 years. So you'd have to live, you know, on the moon to miss what we went through, you know. So, okay, go ahead. Avionics, very simple. Go ahead. You know, avionics and software, it's a different world today. I'm a mechanical engineering guy, so that area has been mystery and is still today. All I know is that there was a fear of these computers. You know, we had 5 computers on shuttle. We had backup flight software. There was a lot of anxiety. We had a very robust avionics scheme where we have 2-fold tolerant avionics on orbiter. So redundancy was required to be test verified, redundant path, you know. and two-fold tolerance for the man or human system became like a mainstay of design. And this is a couple of years ago. I say, well, you know, we did actually, the orbiter system was robust, and we did very well in orbit avionics, but boy, did we do more than necessary. So on the next page, we sort of, suggestion was, go ahead to the next one, David. You said, you know what, especially like for the rocket, when you have low exposure time, don't just do two-fold tolerance and you know, because it's easy. Be smarter. And we said, maybe tailored level of fault tolerance could be a better solution. You know, well, actually, Constellation pursued it even farther. And they, I don't know if you guys know what the scheme is, but go ahead to the next chart. They are using tailored, but they went actually in some of our SRB guys' thoughts, maybe we think they are almost too courageous, you know, where they say, well, zero fault tolerance for mission success, one fault tolerance for, you know, crew critical systems. And then they are adding to whatever extent the mass limits on Orion will allow them. So they went almost, they didn't, I don't know if they listened to my suggestion, but they went far the other day. But they have this new thing, loss of crew or loss of mission, that drives redundancy. So they try to do it wisely. But so they do a different approach, and of course, Orion mass and Ares performance issue constrains redundancy. They can't really do two-fold tolerance, or the Orion would be too heavy. So they're struggling. And so there are some concern about robustness of Orion avionics because of this, you know, NASA new philosophy on the tailored approach they took. And limited, and we also are concerned that limited redundancy we expect it to increase life cycle costs. You will have to pay more attention. You have fewer redundant system. You have to pay more attention during checkout, and you may experience more frequent aborts on pad or in flight, and you have to come home because you don't have enough redundancy to bail you out. So yes, they and I don't say they listened to shuttle experience, but they went what we recommended and even farther.
You know, we're basically following what the NESC laid out in their new DDT&E guide, the zero-based design concept. Now, Orion had to back into it, but Lander has been built designed from the start that way. Start out with a zero-based vehicle, minimum functionality, no fault tolerance, never fly it, and then add back in redundancy, first priority on lock and then with LOM, and in the end you get a better risk-balanced design. The design commodities are used more wisely to get a more reliable vehicle.
You know, I feel like if this LOM really gets some teeth, this could be a very good tool to figure out what is the minimum amount of redundancy you need. And I feel like the LOM is still in the stage where I'm not sure how much design decision it drives. I don't know the guys are comfortable with it, that they understand it. It's a new thing for NASA.
It's driven lots of design on Orion, on Ares, and talk to the project managers. They can show you their lock-on numbers. They can show you what dominant risk contributors drove design changes. I mean, it's very well embedded in.
I'm dying to get your level of confidence in how well LOM is used.
My lack of confidence is more in the fact that, again, we're doing a whole bunch based on analysis. And depending on how well that analysis is calibrated and how correct the analysis is, we'll make the right decisions. But it's analysis. And when we fly, we'll probably find that some of the analysis was not.
Test and then fly, So this is, they went, Constellation went, I don't know if it's a lesson learned from shuttle, but they're doing differently, more courageous, requires you to be smarter. That one, I'm sure you agree with me. The Orion and Ares approach requires you to be smarter about reliability of components, reliability of your subsystems, because you have fewer redundant pairs covering your skin for your ignorance, you know. Okay, let's go to the next one. Next one is operational. This is the one that I'm ready to bend my, is that the expression, bend your pick or something, or break your, you know, I have some very strong feeling. And I've shown these two pictures to everybody at NASA, and you guys may have seen it. This is our little naive way we are going to design this orbiter so we can put it in a bay, and a few guys in a white little outfits, you know, are going to be processing it before, you know. Huh?
It's kind of like that.
So well, you know, interestingly enough, and I don't want to be rambunctious or anything, but the new schematics of some of the processing of the constellation hardware looks just like this. Just like this. Somebody showed me that the other day. Say, hey, Bo, here is your picture number 1 for payload processing at the Cape. Well, I guess you guys, if you guys been to OPF, this is symptomatic of why it takes 17,000 people to operate shuttle. And you know what? When I first showed these two charts to De Castro, who was running, program manager USA, I said, Howard, don't be hard on yourself. This is not a reflection of how you guys operated. This is a reflection of how we designed to be operated. We designed, dropping the landing gear. It's like giving a birth to a kid. I mean, it's so complicated. It's like you have to have a team of doctors around it. I mean, you have to, the tile around, the seals are so complex. You can't just drop the landing gear and pick it back up like you do an aeroplane. It wasn't designed to do that. Access to I mean, it's all on and on and on. And the question is, and you see, I'm going to talk a little about what I have learned, and I'm not sure I was able to convey to anybody at NASA from sea launch. The Soviets have done something completely different. And and so I'll talk about it. But anyway, this is a dilemma that we have created. We think we are designing something, and then we send it to the ops folks and say, well, they're smart, they'll figure out how to do it. Well, of course they will. And that's what they wind up with, And that's what has been eating NASA's lunch, $4 billion a year, 17,000 people, And yes,
what are the touch labor hours to turn around an orbiter?
It's about 500,000 hours, if I remember, 500,000 hours. And I guess you can do your own math. Your contractors' rates,
It happens. I mean, I just read in Aviation Week that the Joint Strike Fighter, and maybe they'll get on the learning curve and this will improve over time, but they estimated the hours to produce a wing, the F-35, it's estimated by 100,000 man-hours.
100,000?
A wing.
Yeah.
So, I mean, it happens.
Yeah. Well, this is, the numbers, I've been away from it for a couple of years, but I remember, last number I remember, 500,000 man-hours to process that, for the standard processing, of orbiter between flights. Okay. So, and this insufficient definition of operational requirements during development phase. Concentration of performance. It has to be, don't put any additional plumbing in the rocket, because that's weights. That's weight. That costs you performance. Even though if you gather all these wires and pneumatics and whatever at one place and had one umbilical, it'll save the hell out of effort at the launch site. But you have to put a little weight in the vehicle where we couldn't. And this is one area that I think I'm afraid that even though there's much more emphasis on operability than was during shuttle development, I still feel much more needs to be done if we are going to wind up with a much more streamlined cost of operation. They talk about, well, we should be able to cut ops cost by half. Hell, we should cut it by 80%. It's a simpler system. Simpler system. Flying what 2-3 times a year. Simpler system. Why are we so not very ambitious? And
so I got to ask another question.
Please.
What is your perception of the biggest cost driver for ops costs? Because we've had a number of folks outside of the SNMA world claiming, oh, SNMA is the big cost driver, and we don't think that's the case.
One of the areas that is a huge thing is lack of commitment to green propellants. And yeah, SMNMA guys, but it isn't because of you guys are evil. It's because the system you were handed. If you did not have oh, the SNMA guys are hard nosed. They tell you have to clear the facility when you loaded hypergolics. Well, of course you do. That's what we did on sea launch too. But if you had green propellants, you wouldn't have to do it. You could have the working. But to me, that's one of the big cost items. And it's just design with insensitivity to how you're going to operate. The leading edge, this leading edge measurement and looking at checking out between flights. It's a big touch labor thing, and it's the way it was designed to. You have to check it. There's this place you have these requirements for these for this out of flattening. I forgot what you call it anymore. So it just hardware was designed to be babied, and we baby it, and you guys are part. SNMA is part of it.
Identify the hazards, and if the program's not willing to accept the risk of those hazards, they inspect. And
yeah.
So it's building a more robust design that doesn't have as many hazards.
I'll show you in a moment how Soviets have done it on this Zenit rocket, and the only reason I'm not trying to sell you guys on sea launch. Like I say, I'm a retired guy. I don't, but I remember being fascinated. How the hell we Americans, and we are just as good or better than they are, and they committed themselves to do something that we don't seem to be able to do. And so I'll get a couple of charts down from now. So okay, so let me talk a little bit about this sea launch, because I know about it. I worked on it for 5 years. It's a platform, modified platform from which we launch. They launch. We say we. I haven't been out of it for 6 years from Equator. And by the way, the first two stages was a last developed modern rocket in Soviet Union before Soviet Union fell apart. First flight was 1985, and Soviet Union, Reagan pushed on Gorby to throw in the head, I guess 90 or 91. So this is a platform, and the other ship, it's a complex of two ships. Go ahead, David. And the ship, we build a brand new ship in Glasgow. That's a concept. And so go ahead. And Ukrainians, which are providers of the first two stages. Now, this is not some kind of a rinky-dink rocket. Lacks kerosene. And I want you to listen to this, because when I talked to Scalise the other day about it, he says, wow, this is great. And then, Bo goes to Houston and falls asleep. He takes naps during the day, and Scalise gets busy doing something else. But I said, Soviets built a green rocket 20 years ago, 30, 25 years ago, that has no hydraulic fluid generation, which normally we use, the hydrazine. And then if somebody wants to know, what are you talking about? How the hell can you control rocket without any of it? Well, they did. And it takes Ukrainians 50 people at the launch site. The rocket was designed, but just one example. All the instead of fueling 3 stages separately, you have a little plumbing inside the rocket, and it comes to a single umbilical. All the pneumatic controls, they use much more pneumatic controls than we Americans do. They run to the same umbilical. So they have the same thing is electrical. Wires, you have a little additional wiring, and you come up with a single 1 T0 umbilical. You know how many umbilicals we have on Ares? I think 9. I was briefing this at Cape. Some kid comes to me and says, well, Mr. Baymo, that's very nice briefing. Let me show you this picture of Ares, 9 manually connected umbilicals for which you have to provide scaffolding, you have to design, so you have to bring a bunch of facility designers, then you have to bring a lot of facility contractors to build the stuff, so you are like, here we are chewing up again money, precious NASA money on ops, and getting ready for ops, because we didn't want to put another 30, I don't know, pounds of plumbing and another 15 pounds of wiring inside the vehicle because we are performance starved. And this is, I think this is, if I see a one short, did we die here?
What causes, Zenith's got major reliability problems though. What's driving that? If you look at the historical launch record, it's far below Deltas, Titans, shuttles, Soyuz.
We lost, on my shift, we lost one flight. They lost 2 flights on Zenith. One was because we tried to kiss up to our customer. They wanted a 45-degree inclination launch. All our launches are due east, you know, from equator. I mean, we take advantage of Earth rotation and all of that. And the guy wanted a 45-degree, and he says, you have to have more precise lift-off time. So we said, okay, well, you know, $65 million guy is paying us. So we went. Russians messed up software change. Didn't close off the helium isolation valve. We lifted off, so it wasn't a rocket. We botched it up. And so didn't close the helium valve. We kept draining helium while we were flying. We went like this through first stage. We were 60 seconds from shutdown on second stage. We ran out of helium. We lost control. So that was one. That one was really not the rocket, nothing to do with design. We botched up the software, ground software. The second, it was not on my shift. It was recently. It had to do with some internal explosion in the engine. They think it's not in the engine, in a propulsion system. They think it's particle impact.
I think even prior to that, Zenith always had a much.
No, you see, this is one of my challenges. Was you and I need to talk. Soviets launched a couple of payloads, which are bags. I found later because I speak Russian, you know. So they thought they fooled us Americans. They launched 2 first on Kamchatka, the peninsula. They didn't want sand to go to orbit. In case they have a mishap, they didn't want to contaminate low Earth orbit. So they saw on Kamchatka. Americans tracking the rockets, they say, they never made orbit. So Russians just drink a little vodka and says, we got them fooled. The first 2 missions were intentionally to land the payload on Kamchatka. So if you look at the track record, I had to deal with this because insurance guys would come to me and says, you had first 2 losses. And so I said so we finally squared it away, but not enough, so public probably still sees those as failures. Okay, let me finish this. Yes, Dave.
We have a little computer problem here. We're going to charge up his machine.
Oh, okay. Let me see. So I got through. So the only reason I'm bringing sea launch is because it was one of my things that I had passion with, and I see these Soviets, you know, designing this system, and we Americans seem to be stuck in this design for maximum performance. You always are starved on performance. You don't have this spread your elbows a little bit to get robustness, so you can do these simple things like combine, you know, like these umbilicals, so you wind up with one, and they have actually one T0 that is connected automatically. And I have, every time I give this briefing, I talk about sea launch, and I even had a couple of tours from NASA guys, you know, they come and they look and say, wow, this is cool. But we never really got this to designers who says, you know what, we could do that easily. You know, and nobody asked me, how the hell do they control a rocket without hydraulic fluid and hydraulic system? Well, they do have their own hydraulic system, but they use kerosene as a working fluid. So they draw from a high pressure pump, a little kerosene, you know, expended in the actuators, and then feed it on the low pressure side. That's how they control first stage. Second stage is different, but none of them, it's all lax kerosene, all the same propellants, no hydraulic fluid, no hypergolic propellants on the rocket. And it's easy to operate, and safety guys don't gain notoriety by imposing requirements, because, you know, you have pretty safe, relatively safe system. Okay, so let's see.
Which way do you want to go?
Oh,
Go back to flight summary.
Oh, this is, oh, you are using from my old briefing. Let's see. Well, wait a minute. I got another stick that I can give you. Hey, I'm one fault tolerant guy, at least. You see.
It's our projector. I think it's 0 fault tolerance.
Oh, it's a projector.
Probably it's projector.
Well, you know what? Let me wrap it up. Actually, I'm 2 fault tolerant. I've got paper copies too. You know. See, I'm from the. Remember, I'm different generation. Yeah. Okay. Okay. So, what you have seen is my thought is that in design for ops, we Americans are not there yet. And you know and I keep telling them, don't be hard on yourself. This initial system, we are just becoming aware. You got some heritage hardware. You can't really operate first stage too much differently than we did on shuttle, you know. But there is so much design ahead of us yet. You know, Earth departure stage, the pieces of Ares 5, all this lunar stuff. And somebody told me, hey, Bo, you are so intense on this design for ops. Do you know what it takes to take a moon of mass to a pound of mass to the moon? And I was just, I don't want to make enemies, so I don't say anything. I say, yeah, I'm sure it's expensive. What I felt like telling, do you know what it takes to operate a piece of gear on the moon? If you think replacing a cold plate at KSC is a bitch, you know, try to do that on the moon. Well, I don't even think that far, you know. But seriously, design for ops. Boy, if you think that we have 10,000 people around orbiter at KSC, you will try to figure how many billions of dollars will it take to replace a trinket on Mars if you want to get that far. Maybe only 1 billion on Moon. Something that, you know.
The time you're talking about going to Mars, the failure rate times the operating time approaches 1. You can't carry enough.
Okay. So let me don't worry about it. Let me just wrap it up, okay? And this is, the chart is called painful reality. You know, we had these 35. I only picked few today to talk to you about, but we had these 35 really powerful lessons learned, and I'm saying. Apart from those, because the ones I talked to you about, or talked to you in the original briefing, was the ones we actually worked out okay. In addition to this, we have 2 design flaws in our system, in the shuttle system. We lost 2 crews and 2 orbiters, you know, and it was not detected and not acknowledged by any of us. We all got trapped into this mentality that says, oh, this is more robust than we thought. Like tile, you know, the TPS, it's more robust. Look, we have flown all these missions. We have these things. We come, we fix them, you know, until one day, bang, you know, and the whole world crashes under you, you know. So I'm saying, so that's what we did. And we had this gap between real robustness and how we perceived it, you know. And we, you know, I sometimes when I used to fly on across Atlantic, I used to talk to European businessmen. He says, you know what, American businessmen, we love to work with Americans. Like they have no limits. They can do anything, and we can. I mean, this is wonderful. That drives us. But I think it also gives us a blind spot. Sometimes we overlook a real minds and we step on them in the process, you know. Because we are so courageous, and Europeans are a little more chicken, if I can use it. I don't want to offend anybody from Europe. They are a little more humble, a little more reserved. Yeah. Okay. So how do you avoid their history? How do you avoid the pain? Well, learn about the past. And that's what you guys are doing. I mean, that's what you guys develop strong system engineering throughout the program life cycle. Griffin really was pushing on it, and I don't know how far he got. Remember a year and a half ago, it was like big deal, rebuild system engineering at NASA, you know, And I don't know whether he is still pushing with the same horsepower or he's, you know, or not. But I don't know that I see the effect of that, you know, developing muscle in the NASA system engineering.
Actually, the Chief Engineer's Office put out a handbook this past year, Systems Engineering Handbook. The NPR came out last year, and this group is going through a systems engineering course.
Is that right?
The first one that the Chief Engineer's
Okay,
Office.
so that's good. So we are doing something at least. Okay, well, that's good. Yeah. And then cultivate this culture of the respect for critics, for dissenting opinion. You know, I said many times, you know, I used to go to me representing Rockwell for system integration contract, you know, with NASA, and sometimes you'd go to KSC, and we had this culture that if it isn't your job, you keep your mouth shut. You know, if I would stand up, or one of my guys would stand up and brief NASA about what we did to get ready for this mission. But you listen to some other projects or contractors, and you roll your eyes, and he says, Jesus, that doesn't look right. But the culture was, you are responsible for what you get paid for, you know what? And I think this encourage people to stand and speak up, you know. But it wasn't, that culture did not, I believe it did not exist, and I think that was not so good, you know. And so what Tommy, how many of you guys know who Tommy Holloway is? He's a, see, there's a guy who has a big name recognition. He was working with me as a consultant. We hired him, we paid him a little bit of money, you know. He worked on these lessons learned from shuttle. And he gave me this phrase, you know, the big lesson. I said, what's a big lesson in this? And he says, we were not as smart as we thought we were. You know, and this is sort of like, for me, it's now easy to say, you know, I've got used to it. It's not easy. What do you mean? We industry, NASA, the world, I mean, is looking at us. What do you mean not us? We were really not. We had all kinds of blind spots, and, you know, and they costed lives and billions, and just, we were, and I think little humility is always good, you know. Feel a little vulnerable in your judgment. It's not bad. So, and knowledge capture initiative, that's new. We didn't have that. Believe me, we didn't have it. We couldn't find this little silly test report from guy, you know, crew person in a crew seat. But it should be practiced as a contact sport. Don't create this wonderful stuff. Create a library that nobody goes and taps on. You have to feed the people who need to know. Don't let them figure out that they need to know, because we are fairly arrogant. When we are competent, you know, we know a lot of stuff. So remembering that you're not as smart as you are is good. Capture, practice this knowledge transfer as a contact sport. And then on this app stuff, you know, I've been harping on this. He said, if you want to save money in apps, don't go after you design a system like we did and we brought two airlines, you know, Pan Am and then United or American, I forget, one is out of business, one is in deep trouble. And we said, well, look at our orbiter and see how you would operate it like you do airplanes. Well, they looked around, snooped around. He says, well, you know, made some trivial recommendation. It's too late. If you want to have an operation like a simple operation, you've got to design for it. And NASA is still holds the key to the app's destiny for a very short period of time. Once you get these contractors online and you sign this thing on the bottom line for this lunar stuff and the Earth departure stage, you will get what you told them to build, and any changes then toward operability is going to cost you money. So you will as well just keep paying through your nose. But now is the time to do it yet. And I've been harping on that for 2 years now. And some people listen to me, some applaud me even. I don't know. And actually, there are some things that are being done. You know, there are things that are done on first stage. There is more attention paid to operability, but not enough, in my opinion, if you guys want this so-called vision to to be viable, you know. And that's all I have. Thank you for bearing with me.
So we'll open it up for a few questions. So let's just start around here at the table.
That's good.
Back here.
Maybe just a comment. I was going to say that to prove your point about operability, I think 25% of the NASA budget is spent on the space shuttle. That's why
$4 billion.
so many people want to get this thing retired and off the books. Because I mean, it's outrageous. You know, it said 1975.
Then we can pay the Russians to.
Yeah.
Yeah. You know, as long you see, it's good to learn to say, wow, so look at those two stupid pictures. You know, probably people think, you should be ashamed showing those pictures. No, I'm going to keep showing, you know, until somebody fires me or not invite me anymore. But you know, if you replace it with a system which is more ops friendly, you have made something. If you replace the one Accord to operate with another system which is equally awkward and expensive to operate, what have you accomplished? You've got a new system. You've got a new fleet. But that's why it's so important to try to make some headways. Go ahead.
This thing we talked about, analysis versus test, SpaceX, their second launch, they lost the vehicle because of the propellant slosh problem in the upper stage. And the reason that happened was their physics models, their analysis, underestimated the loads of the separation of the upper stage. And so it caused a dynamic in the tank they didn't expect. They had more slosh than they expected. But it was just an interesting example, another example of how relying on analysis early on, you're going to miss stuff. Now, in their case, they're testing tons of rockets and engines, so it's a good data point for them. We only have 2 flights right now on the books. We're only going to fly this vehicle twice before the crew gets in, and they're trying to delete one of those flights. So how many of those things are we going to miss? That may or may not show up on the first launch.
Yeah, I didn't know that. I never heard that STS-1 story with the RCS tank.
It buckled, you know, it didn't break. You see, if that load was in tension, you could have ripped off this damn, you know, because the structure, you know, you buckle, but you still carry some load. If subsequent loads were lower than this load due to ignition overpressure, you're okay. And that's what apparently happened. You know, we were able to land, you know, and but if it was in tension, we would have had a catastrophe.
How many of the first 5 flights did we have near misses on? You mentioned STS-1.
Well, we had STS-1, we had 2. We had this aero anomaly and ignition overpressure. You say 5?
I'm just thinking, within the first 4 or 5 flights, how many of them do you think like we had a near miss on? Because people look at, when we try to say you need more than 1 flight before the crew gets inside, they say, well, look at shuttle. We didn't have any failures in the first 5 flights. And we point to the launch data for all launch vehicles, and it shows quite clearly you need 3 or 4 flights until the risk is brought down.
Yeah. Well, you know, Dick Slayton, you guys remember Dick Slayton. He stood up at the STS-1 FRR, and he says, you know what, my experience, and he was an experienced astronaut, and he was a manager, I mean, he was a smart guy. He says, you know, the 90% of the risk in the first flight, next 5% in the second flight, and and then the remaining 5% is distributed through the rest of the flights. Look what happened to us. We survived first and second, so supposedly we eliminated 95, according to Dick Slayton. I don't mean to impute his logic. It was probably valid, but our experience was completely different, you know. Look, but the Columbia could have happened, you know, on STS, any. Go ahead.
My question relates more to how you captured the lessons learned from these experiences. Did this occur after the fact, during a review process, and then you collected the information, made it available, or how did that happen?
Well, you know, I think you guys got the forum, you know. I thank you very much. I did my job. I mean, seriously, I thought, wait a minute, Bo, you're retiring, do something, you know. So I was a Boeing guy then, and I wasn't, to be honest with you, I wasn't trying to market anything. I was thinking, well, you know, how about you will have fun, you'll meet some new people, and do this useful thing. Now, telling people about it versus seeing somebody doing something that comes out of it, boy, they are like far apart from one another. You know, like some of the things that are happening on Constellation, somebody could claim, well, that clearly came from shuttle experience. Well, maybe it did, maybe it didn't. Maybe people, just smart people doing something a little different and wiser. But it's up for you guys to figure. But the key is get to knowledge to the people who can actually use it. Like, you know, these umbilicals I've been bitching about, you've got to talk to umbilical designers. Talking to Doug Coog and Doug Coog and Horowitz is fun for me. You know, they're high important people, but they don't design any umbilicals. You know, you got to get down to people who actually can use it, and you guys will have to figure, how do we do this? How do we wake up the guy who is sitting there designing and says, you know what, we think you ought to look at this. And your first impression will be, well, I'm too busy. I'm designing umbilicals. He said, no. So you guys have to figure this out, how to cause attention from the guys who can actually affect something.
One of the things that we want to do is, along the way, this is looking forward, is capture what worked and what didn't work in terms of mitigating our risks. How did the risk track over time? What were some things that we learned? And the eco-sensor risk clearly was something that has been discussed a lot in the past year. And it's one that we want to capture. I think KSC's done a good job at capturing video and other means. But do you want to say something, Mike, about that one?
Not really, but I will.
Yeah, that's a really, yeah, that's a terrific one. Yeah, yeah.
I guess I missed the beginning of the eco-sensor issue. I got the climax of it, but we had carried this risk on the books for a while for this intermittent failure. And when I came in, SE and I had a shotgun approach to trying to fix this failure. And they ran through their mitigation plan, said that the mitigations had reduced the likelihood of this risk, but we hadn't understood the root cause of the risk yet. And ended up closing the risk at the top risk review prior to the flight that we had to stand down for eco-sensor failures in December. And in the end, it turned out to be another sidebar is we had an extensive discussion with the SE&I folks about what the probability of risk was, because our analysts were quoting a fairly high probability due to common cause failures. And SE&I was convinced it wasn't a common cause failure, and therefore had a lower risk likelihood. And in the end, it was a common cause failure. Had we looked to another program, had we looked at the Atlas history, we might have had a chance of figuring out what this was, had we looked outside our programs.
Well, that's a wonderful example. You know, when you were talking about this, who's the SNMA chief at headquarters, astronaut?
Brian O'Connor.
Brian O'Connor. Yeah. Wonderful gentleman, smart, like insightful, you know. It was before Columbia flight, and I was at the readiness review. He was grilling guy from a tank project who stood up and says, the foam hitting orbiter is inconsequential. No, they were talking about these ramps, these big PAL ramp. And Brian's question said, wait a minute, there is an integrated hazard that says accepted risk hazard, but it was based on a popcorn type quantity. And this is not a popcorn. And you know, and he pushed on it, but somehow climate in the room wasn't, the senior managers didn't take the lead from his prompting, and the thing like discussed it and it went away. And I sometimes I wonder, you know, it takes so much courage, and you have to know. I mean, you can't show up in this big room of 150 people at flight readiness review and be convinced and convincing to others that you're right, you know. it takes some incredible personal courage, and I'm not even sure. I don't know that I have it. I don't know if any of you guys have it. It takes a lot to stand and, like, you know, be on, because you can get fired, you can get stomped on, you can. So I don't know what it is, but there is an element in stuff like this, a conviction and courage to stand up and just be unwilling to back off, you know. But I don't know that we have in our culture that, you know. Okay, guys, you were a great audience. Thank you.